Yeah, I've got Adam Smith here. Very excited to have him here. We had an intro talk and we had a very interesting time. So Adam is a professor of computer science at BU at Boston University. He got his PhD from MIT in 2004. Was a faculty member of Penn State 2007 to 2017. Interested in obviously data privacy, and cryptography and connections to machine learning, statistics, information theory, and quantum computing. And he's received some amazing awards: Presidential Early Career Award for Science and Engineers, the IACR Test of Time Awards in 2016 and 2019, and the 2017 Gödel Prize. I'm going to let you talk about those if you want to, Adam, but you've also got some slides I think we're going to go through. So over to you.
Thank you. So what I'd like to talk about is this problem of privacy in statistical databases, and we'll sort of dive into one aspect of this that came up in the previous session with James Honecker and Mercedes Crosas, although we'll dive into a more specific aspect of that in this talk, and so it should be interesting, I hope, even for people who attended that, and accessible even to people who didn't. So it might be helpful to consider the problems specifically faced by the U.S. Census. So the U.S. Census Bureau collects information from many, many individuals as part of its decennial census, as part of the many other surveys it runs. And it has a responsibility to make the information it gathers as available as possible to outside researchers, to government agencies that need to make decisions. But at the same time, it has a legal obligation to protect the information of individual respondents. And so it faces this trade-off between making the information as available as possible and protecting confidentiality. There's, the Census Bureau is a kind of a notable example of it, and one that's been in the news a fair bit recently in the United States. But really, the same problem at the level I described it comes up in many, many places. There are many times when you have some organization that's acting as an agent, collecting information on behalf of many people and trying to make that information as widely available as possible, or at least available for certain types of analysis. Okay, it comes up with medical and public health data. It comes up with information from social networks, information about educational systems, and at even at a technical level, information about how people are using certain systems, either how customers in a cloud data center are using the data center, or how individuals might be using a mobile app and using their mobile phones for various purposes. Okay, so in all these areas, we've got this balance that we need to understand between a desire for accuracy and a need for some kind of confidentiality. And really, I'm interested in trying to understand this problem and, as much as possible, analyze it really rigorously, make clear and refutable scientific statements about the kinds of guarantees we can and can't provide. Okay, so just to frame this, something that many people would have as their first instinct if they had some data set that they wanted to make available. The thing they might do is say, well, I'll just take out of this data set anything that's obviously identifying. So if I'm the Census Bureau, maybe I remove names and exact dates of birth, but I would leave in, ages, maybe coarsen to a range of ages, or other things like that. Or for example, if I've got a data set of emails that I would like to make available for training, language prediction models or something like that, then what I might do is remove, specific names. I might remove anything that's obviously identifying and try to leave whatever's left. Now, the first problem you get with this type of approach is, of course, you may be scrubbing the very thing that people are interested in. For example, if you've got a data set emails, then you might need, you might actually be most interested in who emails whom. And at that point, this has been scrubbed from this particular version. And also there might be entire texts of emails that are sort of too sensitive to kind of release in any real form. Maybe the more subtle problem, though, and the one that I find more interesting, is the fact that this attempt to just remove obviously identifying information just doesn't work. Okay, so as an example, let's consider the following photograph from I've helpfully grayed out the face of the subject of the photograph, but most people, especially in the United States, but even abroad, would be able to identify the person in this photograph pretty easily and within a couple of seconds. And that's because even though I've grayed out his face, there are all sorts of other clues there that we can connect to other, external sources of information that we can use to identify the person in the photograph. Okay. And in some sense, this is the problem with attempts at anonymization, is that when you're kind of when you're attacking these things with, say, computerized databases, everything has these little handles you can use to connect to other places. Okay, one fun failure of anonymization is in fact comes from face blurring. So people showed you can train AI on blurred faces to actually recognize them. I've got a few other examples. There's a nice study from a few years ago where they showed how DNA could be just genomic sequences could be used to predict last names of men with reasonable accuracy. There was a case of data, a taxi ride data set from New York City where riders were re-identified. There are lots of other examples out there. Okay. The morals I want to draw from these examples is that in some sense, everything's an identifier. It's very difficult to put your finger on some piece of information and say this wouldn't be useful to help identifying a person. Okay, and the people we're worried about exploiting the information we release can have access to other sources of information that we don't necessarily anticipate. And as a result of these problems, attempts at sort of straightforward anonymization are regularly broken. Okay, now you might say, well, maybe the problem is that we're trying to release granular data. Like maybe if what we did if we were only to release aggregate statistics, we'd be okay. And the issue is that even that is problematic, and the problems hinge on the difficulty of pinning down by what it is that the word aggregate means. The issue is that aggregate statistics taken together can encode data in really surprising ways. Okay, so a trivial example is that if I tell you the average salary at a small company before and after some particular person resigns, and you know how many people work at the company, then just from these two averages, before they resign and after they resign, you could figure out exactly how much they were making at the time they resigned. And machine learning models increasingly they're trained on very sensitive information, and they're very complex, and they reveal all sorts of stuff. Literally cartoon example is due to XKCD, where this group of revolutionaries is caught by the location of their meeting is revealed by the Smart Compose prediction feature in Gmail. It's a silly example, but actually they're real life examples of language prediction models that were trained on sensitive data where they spit out exact phrases and identifying phrases that from the corpus that they were trained on. Okay. So there's lots of research in general on trying to understand how to breach privacy based on different kinds of released aggregate statistics. The moral that I want to draw from these is that in some sense you can't release everything everyone would want to know. Okay, if you want to release really rich and sensitive data, if you want to analyze rich and sensitive data, there is a real trade-off to be wrestled with. And so we need precise tools for quantifying that trade-off and addressing it. So my work is exactly on that topic. I look at trying to pin down what we mean by privacy when we're releasing information about a sensitive data set. I look at designing algorithms that satisfy these definitions. I look at trying to design attacks that break weaker variations. And I look at there are various interesting connections to other areas of science that I'm not really going to talk about. So let me explain one idea that's called differential privacy, and then we'll turn it over to the conversation. So differential privacy came up in James's talk. So it's the basis of a number of existing deployments. There are deployments in Apple and Google, also now Facebook and maybe some other companies, a number of startups. The US Census Bureau will use differential privacy for differentially private algorithms to produce the public use data products from the 2020 decennial census. And it's a burgeoning field of research in computer science and beyond into topics like law and policy. So here's the basic idea of differential privacy. It's based on a thought experiment. Okay? And the thought experiment is to imagine what would happen if I were to take my data set and run my algorithm, but after having changed or removed one person's data from the data set. So imagine on the left, we have sort of the real world, we have a data set, and some algorithmic process is run on that data to produce outputs, possibly in response to queries coming from the outside. And in the green world, we've gone and changed person 2 to some other alternate record. And the question we'll ask is, how much does the distribution on the outputs of this algorithm change? And, for example, let's say I've got two probability distributions. These are kind of fake examples. The distribution on outputs I would get in the blue world, and the distribution on outputs I would get in the green world. And what we'll ask is that for any possible set of outcomes, they should occur with about the same probability in these two worlds. So this is going to be our criterion for whether or not this algorithm A is differentially private. So here, differential just refers to the fact that I'm changing one thing in the data set, one person's record, and I'm asking whether or not the kind of set of outcomes, the probabilities of outcomes, change a lot. And what the real meaning of differential privacy is that what it means that no matter what an attacker knows ahead of time, they'll learn almost the same things about a person in the data set, say me, whether or not that person's data are actually used. So whether or not my real data are used or just some fake record dummy record were substituted for mine, an outside attacker would learn the same things about me no matter what they know ahead of time. So that's a very strong type of guarantee, and it leads to various nice properties of differentially private systems, and that's what's led to their adoption and their study. So I'll stop here, but I just want to. My last thing is just a couple of places where this might show up, and this I'll turn it over to Mike as to how he wants to lead the discussion. But places where this idea turns up, you can imagine, for example, if you're analyzing some shared data set, possibly a virtual shared data set that doesn't exist in one place, dealing with real-time statistics on cloud systems, or alternatively running distributed surveys as we're now doing, where we're trying to collect information about self-reporting of COVID-related symptoms. So I'll stop there. Thanks.
Thanks, Adam. Loads and loads of things I want to ask, and not just the stuff we talked about before. You've just raised loads more. Well, start with a kind of a concrete thing. It's just, what can you give me some examples of this actually happening out in the wild? Is this something which is mature enough that it's actually being used? And if so, Have you got some good examples?
Yeah. So like I have an iPhone, and that the iPhone Apple collects information about certain aspects of how people use their phones that they consider too sensitive to or
Sure.
to store that information explicitly. So they collect that information via reports from the phones that are differentially private. So that in that case, the algorithm is being run on the phone. Google's Chrome browser does something similar with certain types of settings information, where Google monitors, in an attempt to watch malware spread, monitors settings via noisy information that's collected differentially privately. And then another good example is the U.S. Census, which is
sure, which you talked about at the beginning.
Which I mentioned earlier, and that's certainly something that affects everybody in the U.S.
So another question which came up as you were talking was, mathematicians and security people generally don't like words like almost. And I wondered if you had anything a little bit more precise you could offer to people on that.
Sure. Yeah. I mean, the definition, as is normal in sort of security context, the definition is parameterized by some measure of leakage. It's usually denoted epsilon. And if I just go back, as I don't have the exact definition on my slides, but I'll give you sort of a sense. So what that means is that for any set of outcomes, what I say is you get about the same probability in these two settings. So mathematically, it's for every data set X, and for every other data set X prime where one entry has been changed or removed. And for every set of possible outcomes, the probabilities of that set of outcomes under these two data sets should be within a factor of, normally it's e to the epsilon, but think of it as 1 plus epsilon of each other. So there's this number epsilon that measures how close to 1 this ratio of probabilities should be. So that's asking how close these two numbers. There are two numbers you're comparing, and you're looking at their ratio, and they should be really close to 1.
And can you design...
And like a typical setting...
Can you design a system or say, I need this particular ratio? Is that sort of the sort of thing you can do?
Yeah, that's normally the way it's done. You say you specify the ratio and you design an algorithm that guarantees that ratio. And it's a property of just the algorithm. You only need to, reasoning about algorithms is not easy, but you only need to reason about the algorithm. There's no implied assumption on the distribution of the data or anything like that.
Okay, that's really interesting. Thank you. So James has asked a question earlier on, which he kind of answered about sort of homomorphic encryption and multi-party computation, and sort of how they kind of complement each other. And that's interesting things. There's another one which didn't come up, which was trusted execution environments, which allow you to run code on a machine you don't trust, so that external parties can't look in. Is that complementary, competing, similar? How would you characterize that?
So, the short answer is they're complementary ideas, and I think the right way to think about these is to think of trusted execution environments and multi-party computation, and also fully homomorphic encryption, as answering the question of like, how can we go about running some particular algorithm on data that's not all in one place, and how can we do that securely? Okay, so what multi-party computation allows us to do literally is run a protocol where multiple participants are exchanging encrypted and secret shared information in a way that allows them to like logically run some algorithm, even though physically the data remains sequestered at the individual locations. The question, and a trusted execution environment offers you something similar, except basically all that, it is the case that all the information is sent to one place. It's just done in encrypted form, and it's only ever decrypted in that silo, and so it's not available to the outside, as long as that trusted execution environment is secure.
It's very helpful. Thank you.
What these technologies don't allow you to do. Sorry, I'm probably being long-winded. I'll try and finish up. What these technologies don't do is tell you which algorithms you should run, and which algorithms are going to be what is revealed by the output of these algorithms, right? So, for example, I gave that the silly XKCD example where the sentence prediction model leaks the information of the revolutionaries, secret meeting. Okay, and so what's going on there? Like, it wouldn't matter whether or not that model had been trained using multi-party computation or a trusted execution environment. The problem is the model itself, the output of that system, just contains sensitive information. So the problem that differential privacy is thinking about is or trying to address rather is like, how do we decide when the algorithm we're running, be it on physical data or virtual data, is revealing sufficiently little information that we're comfortable, making that output available?
Sure. So we're running out of time on this stage, on the main stage, but we'll have a session going on afterwards, to which people are very, very welcome. We're going to be delving a bit further in. But the answer you just gave me actually leads me on to another question, which is, beyond having 20 years experience in the field, how can I, a relative lay person, know whether a particular problem is likely to have a good fit to differential privacy algorithms and techniques?
Yeah, that's a good question. I think that is a question whose answer we're still trying to understand as a research community, but we have the answers in broad strokes. So, roughly speaking, you should be asking, this thing that I'm trying to do, does it depend heavily on one or a small number of people's information, right? Would it be useful if in the hypothetical setting where somebody was dropped, right? So, for example, if the thing I am trying to do is to give you the names of the high influence people in a social network, that it won't be possible to do that differentially privately, because the thing you are trying to reveal is exactly individual level information. On the other hand, if I'm trying to reveal, what's a rule, what is the correlation between someone's the size of their set of friends and how diverse they are, and the kind of some measure of influence in the network, that is the kind of thing, if I'm asking for that sort of statistical level information, that is the kind of thing that does fit differential privacy well, or potentially does. So we don't always know. There's still a research topic for various specific computations to figure out the best way to do them differentially privately. But at that level, we kind of understand the type of thing where
there's still a job for you to be done. It's not as if you can just retire now. So I guess we should carry on where we left off, if that's all right with you, Adam. We've got about 25 minutes.
In fact, given that it's a small group, I'd be fine with having people join by video if it's meant to be kind of more of a...
Yeah, I don't know if we can do that. If we can, that's fantastic. And at the very least, people do ask questions via the chat. I'm tempted to put some polls in, but I suspect that if we do, we're going to be leaking lots of data. So it's going to miss the whole point of the
too small a sample size for privacy.
Yeah. So while people are thinking about what they want to ask, let's if you could mute yourself when you're not speaking, that would be great. Thank you. Sorry. So another question that comes up is, can you talk about the difference between enforcing privacy guarantees at the collection stage and enforcing them later? Because I believe there's a difference, and maybe you can kind of explain that to us, and maybe some of the benefits or down.
So when we say enforcing information at the collection stage, so maybe one thing that I tried to say, but that maybe wasn't explicit about, is that, to satisfy the kinds of guarantees I've discussed, you need to introduce some randomness, some distortion or error or noise or sampling into the algorithm. And the question is, where is that distortion or error applied? So one model is like the census model, where all the information is ingested into one central database. And then it's processed and noise is applied sort of very carefully to intermediate computations, and then a final product is put out there. In the case of the census, that's a synthetic data file that is formatted to look like the real data file would, but was produced by making a series of kind of noisy measurements of the real data file. Another model is, say, what things like Apple use, where when information is collected from my iPhone, randomization is applied to my data by the phone. And what's collected by Apple are these noisy reports, these kind of noised up values, which bear very little relationship to my individual response, but which kind of in the aggregate, if you have a lot of them, allow you to nevertheless clearly see and estimate global trends. So for example, I might, even though I can't get a strong signal on whether what you typed on your keyboard, if many people are typing the same new word, right? Then that will, Apple can learn that at this aggregate level and add it to their standard dictionary, for example. So the difference is whether or not this kind of noise and distortion is applied on centrally collected data, which requires either a trusted collection point or these kind of cryptographic solutions along the lines we were discussing before, or if it's applied kind of on the phones, and that leads to a better trust model in the sense that I, as a user, only need to trust the software on my phone is working correctly. But on the other hand, we know this leads to lower overall accuracy. We need more data to get the same level of accuracy.
That's a really interesting trust model, given how much Apple control what goes on their phones. But I take your point. There is definitely a different trust model there. Okay, that's really interesting. Any question? We have a question from William. Let's have a question.
Yeah. So how much do you think? Because there's obviously two struggles going on within organizations like Apple and Google and others, and I'm trying to figure out which way they would lean. I mean, why would they care about privacy-conscious algorithms, except for their consumers want it, but they don't really want it because their apps work way better and they can provide better services. So there's this tension between privacy and convenience or knowledge and information, and I'm trying to figure out.
There's another thing in there, William, which is that plausible deniability is a useful thing. So I'll hand over to Adam, but that's just
so I'm not going to speak for Apple and Google, although I know people who work at this company.
Any organization that's, for example, building an app, right? That might be gathering data.
I think there are a couple of things that are in tension. So on one hand, as a developer, I want to get as much direct access to how people are using my system. Certainly, if my business model involves selling advertising, then I can do that better. I can do that more easily by just collecting all the information. But it's not. There's a growing realization, I think, at these companies that there are downsides to having all this data. First of all, it creates bad optics, PR. It puts them on the hook for data breaches, potentially. It puts them on the hook to be subpoenaed for stuff they don't want to be subpoenaed for. It creates all sorts of operational costs that they don't necessarily want to incur. So even even completely selfishly, these companies, I think, have various incentives to do this, at least for certain kinds of information. Notice Google doesn't do this for like ad tracking. That they collect everything they can and they keep it all because that's their business model, right? But what they are trying to do is trying to identify pieces where they don't need to do that if possible. And so like an example of that, there's a big effort at Google to build like distributed language models for like sentence prediction, for example, and speech recognition on the phone. And that kind of thing, they're trying to train those models subject to these types of strong guarantees. So, of course, there's tensions within the company and there are lots of different forces at work, but they don't all pull against privacy.
Interesting question, interesting answer. Anyone else have any questions? Callie, Mark, I know you've probably had lots of chances to ask Adam questions in the past, but Callie, I don't know if you have anything.
I'm happy to see a few faces I recognize.
Yeah, how's it going?
Oh, Callie as well. Okay.
Yeah, I'm Boston. I'm BU as well.
I am BU and Red Hat.
My grader for is a grader for an algorithms class, I thought.
Yeah, I was just curious. I was curious to ask about which for the noise, what type of cryptographic like algorithms or what are being used right now for that type of noise?
Yeah, so the ones that are, there's lots of stuff that's in research papers of varying levels of complexity. The ones that are most commonly deployed are come in a kind of basically two varieties. So one, if you're looking at things that are done in like on device in this kind of very distributed model, what they're roughly doing is, they're doing fancy and modern versions of what is called randomized response. So this is something from the 60s where let's say I ask you a sensitive question, think back in the 50s or 60s, if I were asking someone, did they ever have, I don't know, sex out of wedlock, and there's no way you're going to get an honest answer out of people asking them directly. And so what this idea was to give people plausible deniability, to use Mike's phrase, was to give them, like, roughly speaking, a biased coin to flip. So imagine it's like a spinner or something that comes up heads with probably 2/3 and tails with probably 1/3. And you say, okay, if it comes up heads, tell me the true yes/no answer to my question. If it comes up tails, tell me the opposite of the true answer. Okay? And you can make it user-friendly in various ways. But what this does is it means that any one there's a reasonable chance I'll have to say yes, no matter what, right? To the question. And so if I do say yes, it's not like actually telling you anything about me. But if, like, say 20% of the population you survey, their true answer is yes, then you will see that, because that'll be reflected in the fraction of people who said yes. It'll be closer to 1/2, but it'll be sort of that it'll behave in a very predictable way. And so that's one type of. What's going on your phone is not quite that simple. So what they're doing is taking some feature encoding of, say, words typed on on the keyboard, and applying this type of randomization to, like, individual bits. So it's a little more complicated than just a spinner, but that's the basic idea. At the central level, what people do, for example, to train machine learning models, deep learning models, is they're adding noise to statistics that are summed across a data set. So, like, a good example is running gradient descent for training a machine learning model. It turns out the gradient can be written as, like, some sum taken across many data records. And you add noise to those sums at each point in this iterative algorithm. So you're getting these noisy gradient measurements, and that's still good enough, if you do it just right, to identify a good model under right conditions for a good predictive model. And so that's like the kind of thing people do. So they're either adding, and the census also, they're either adding noise to things that are basically summations across data records, or at the individual level doing this kind of randomized response thing. And then estimation process is more complex.
Do you ever want to combine those, or is that not generally helpful, or does it make it difficult?
Usually systems are kind of at one end of the extreme or the other. They either have a central thing they trust or don't. But yeah, certainly in research papers, people have investigated what can you do in some sort of hybrid model where, you know, maybe some people opt in to the central data set and others don't. So you've got some fraction of your data, you know, that you have only this very kind of very noisy access to, and some fraction of your data which is collected centrally where you can run these more sophisticated things. And there are benefits to that. Mike, you're muted.
More questions? I've got loads of questions, but I want to give people a chance to. William,
we'll let you get one in, Mike, first, and then we'll think of some more.
Well, yeah, one is actually, you know, we've been talking about this stuff. This is Red Hat. How much of this is open source?
So certainly the implementations used by Apple and Google are not open source. However, Google has some version of what they do that is open source. And the overall movement is towards open source. So OpenDP, which James Honecker talked about just before I joined in, is a great example of that. So that's recently launched. I mean, just kicked off at the beginning of this calendar year. But before that, even before that, Google, for example, made this. There's a sublibrary of TensorFlow. So TensorFlow is this, you know, Google deep learning thing. So there's a module within TensorFlow for training differentially private algorithms, and that's open source. And it's I think it's not exactly what they use internally at Google. It's some, you know, slightly different version of that. But there's certainly an attempt to let people inspect the algorithm. So what they do say is it's basically the same algorithm, even though the implementation is not the same. And so they they see it as a real advantage when they can get the kind of stamp of approval that comes with public scrutiny on the algorithm. So it's definitely there's a movement. And and Facebook also. Facebook just came out with a module for PyTorch for doing differentially private learning. So that's, you know, that is something that like is generally thought of as the de facto standard is you should make at least some version of your implementation.
Well, I mean, if you can't make it open, then how are you supposed to trust what you're getting out? I mean,
well, that's something that people criticize Apple for a lot. So Apple doesn't have much of a corporate tradition of openness, and
I have a colleague who's just joined them to work on open stuff, so we'll see.
Yeah, they're changing, and also they're doing a lot more kind of academic style research, which I think lends itself well to a more open model, obviously.
Security more like from an academic standpoint, your definitions of security, even the fact that like any adversary can knows what you're doing to create your algorithm. And so by not having your algorithms public, it kind of seems like it's defeating the purpose, or the definitions of basic security.
Yeah, well, you want scrutiny. I mean, the model in security is you should assume that the algorithm will be figured out by your adversary. And so you may as well make the algorithm available to everyone so that, you know, white hat hackers and everybody else can help you spot problems. That's the meta reasoning that one is normally given.
The big argument that we make, like in the Anarchs project, is you also derive some trust from it being open.
Yeah,
right?
yeah, exactly.
It being open.
The other thing is makes it easier to evolve standards, that's something else that's going on in with differential privacy. And so there are lots of good reasons. I mean, certainly as an academic, I see it as all upside to make things public. I understand why companies are more reticent to do that.
There also needs to be some more governance around the data, right? Like almost some sort of a vault of who's allowed to see it, because one can imagine that in someplace like Google or Apple, and probably like this probably happens all the time in China, right? Where you have this huge amount of a data pool where, let's say Apple and Google have lots of best intentions and people who are doing privacy conscious algorithms and all that sort of stuff. But the pool of data is there, and some other group, they don't care. Their job is completely different. Their guidelines are different. Their privacy concerns are different, and they have access to the same thing, and they could be using some of the privacy algorithms.
Well, and that of course is the argument, the law enforcement argument, isn't it? If the data is there, then law enforcement will get at it. It doesn't even need to be in the same organization.
Right, and you may not need, to Adam's point earlier about removing certain identifiers, but if you've got data from this pool and data from this pool and data from this pool, suddenly identifiers become really, really easy, because you may have removed it from here, but there's something over here that can identify you from over there, right? That's that sort of thing too.
Yeah, so one of the, this is where, these cryptographic technologies can come in, is that, one of the complications of this is, like, it's certainly the case that the algorithms that run in this sort of central aggregate model with one trusted database, they're much more accurate. And so one question is to what extent you can get the benefits of that model without actually pooling your data in one place. And that involves lots of connections to things like homomorphic encryption, multi-party computation, and potentially trusted execution environments. Another issue that, like what you were saying, that sort of a different angle is to the more like the organizational aspect. And there, it's interesting that actually there are deployments, I didn't really mention this, but a number of deployments of differential privacy are actually internal at companies. And they are intended to provide, to firewall off data sets within the company to allow, let's say, somebody who wants access to the data from another part of the company to get what they need without just giving them the data, without having the data. At a 40,000 person company, you can't assume that everybody is actually trustworthy. And so minimizing the number of people who actually have access to the raw data is important. And that is one of the ways in which this type of technology is used. Like in particular at Microsoft and I think at Facebook.
So we've got about 5 minutes left. I want to give Adam you a chance to sort of wrap up anything you want to say. And I guess one of the questions too that we haven't really talked about is how is there a balance between sort of bits of the field that are mature and bits that aren't? You said earlier on that there's loads of work still to do, so you're not going to have to retire anytime soon. But, where are the areas that you would say, this is pretty much understood, we know how to do this, as opposed to, frankly, no one has the slightest idea how to do this right? Do you see what I mean? It's the... Oh, you're muted again.
I mute myself when I wasn't speaking. Anyway, a lot of the successes where the places where the methodology is better developed come from these sort of relatively straightforward descriptive statistics. Let's say of the type the census might produce from the decennial census. So those are tables that say, for each census tract or block, how many people live there, what fraction of them are African American, women, children, that sort of thing, age distributions. Where it gets, where one of the places that is still at the frontier of what we can do is sort of training these very complex very complex machine learning models, and language models are a great example because essentially the state-of-the-art ways of doing this, if privacy is not on your kind of list of concerns, is to train these huge models that are, they are literally like terabytes of information, and they they don't fit on old hard drives, right? They're like, just the model, the description of the model is enormous, and they memorize information like crazy. We know this, and there are various reasons we have to think that they have to really get state-of-the-art performance. And so understanding how close we can get while not kind of just putting in people's information there in the clear is, definitely something, we're not there yet. So that's an
big edge of research. Okay.
And then a related thing is sort of with these surveys, very complex surveys where you're measuring lots and lots of different things. Again, so like the census, for example, runs the American Community Survey, what used to be called a long-form census, so where they, for a small subset of the population, they ask much more detailed questions that get at, income and marital status and just all sorts of stuff, very personal stuff. And that is, understanding how to make the results of those kinds of surveys usefully available and yet, preserve privacy. That's something that is, an ongoing topic of research, and one that, has problems, all sorts of open problems, both at the theoretical level and also at the kind of practical level.
Excellent. Well, thank you very much indeed. We've got sort of 2.5 minutes. Any final things from you, Adam? If not, any final quick questions from the folks here?
I have a quick question.
Go on,
Adam, what do you do with your phones and stuff to try to limit your any quick tips on cheats for limiting your keep your privacy?
I try to use them less.
Yeah.
Take the batteries out, throw them down a well.
Right. Well, I don't have like a little Faraday cage bag for my phone, but I do try to limit its use to a relatively small set of things that it's good at. I'm actually not that sophisticated, in my kind of the effort I'm willing to spend in limiting in like making sure all the settings are where they are. And so, I try to, but I'm sure there are people who could give you better advice, but I do try to read the, to the extent there are privacy settings that we can read and use, I try to read them and, figure out like what I can set.
But isn't it sad that there are few apps, like if you want to download an app that much, like that you're downloading it, chances are when you read that privacy thing, you're like, oh, I guess I'm okay with that. Yeah. Particularly when you're...
The state of these things sucks, let's say. And also the extent there are so many platforms that you just don't have the choice. Like my car, I can't plug my phone into my car without it trying to download my contact list. And I'm like,
oh, I know. Yeah.
That sort of thing is super annoying. That's why I ride a bicycle.
Yeah. Excellent. Well, thank you very much indeed, Adam. Thank you, everyone, for engaging as well. There's been some fun stuff on the chat as well. I'm really concerned about some of my colleagues now. But it's been lots of fun. Thank you so much for your time. Thanks for everyone getting involved. Thank you to Adam. And catch you around.
I wasn't even reading the session chat. Yeah. Okay.
Fascinating stuff, Adam. Thank you.
All right. Yeah, no problem. Thank you all. And Callie and Mark, it was great to see your faces.
Thanks. Bye-bye.
See you around.